So these are some steps to start a simulation. But I'm not going through too much in detail because actually you know most of that after going through the case study. The first is to decide what components you have. So maybe you have nitrogen, hydrogen, methane, water. You define all these components. Then you choose the thermodynamic model. All right, you choose the thermodynamic model. After that, you draw in the unit models. You draw in your pumps, your heat exchangers, your separators, your reactors. Then you connect streams to them. So this is an inlet, outlet. Then you run the simulation. And then you check the results. So it's actually quite simple if you think about it. But it is actually like programming the unit operations itself that is the most difficult part in any process simulation. In process simulation, I would say two items are the key. The first item is to know the thermodynamics of your process, because you need to choose it. You have to choose the correct thermodynamic model. In HYSYS, they call that fluid package, but generally we just call thermodynamic model. Using the same thermodynamic model, using different process, even using different software, the result should not differ by 5%. Usually around 1 to 2%, but less than 5%. If your result differ more than that, there is something wrong in your simulation. So that's usually like the standard that we hold ourselves to. And you do need to have some basic knowledge of what are thermodynamic models before you choose. Otherwise, you won't know what to choose, like, and you can't just choose ideal guess. You can't just assume everything is ideal guess. You have a very, very inaccurate results. In oil and gas applications, the most common equation of state, which is a type of thermodynamic model, is what we call the Peng-Robinson model. Peng and Robinson are the inventors of this model. The second is the Swarth-Wheatridge-Kwong model, or SRK model. So usually people just call it PR, SRK. So when you're solving some thermodynamics problem and your temperature is slightly different, don't panic, because it's sometimes just an issue of the calculation method used by the simulator. But it should not differ too far. So let's say if one simulator gives you 150, the other 147, is actually acceptable. It's still within this range, right? So don't panic if your friend gets another result and you don't. It is still within the acceptable range. So these are the two most common equation of states in thermodynamic models used in HYSYS. The first is the Peng-Robinson model. The second is the SRK or Swarth-Wheatridge-Kwong model. So what exactly is this model, you ask me? Maybe you have not taken thermodynamics as a subject and you ask me, what exactly is this model? So basically what this model does is that this is the model actually. The first equation here is the model. And what this model does is that I want to know what is the volume of something at certain temperature and pressure. That's it. That is what the model tells me. Substitute in P, substitute in T, get V. That's what the model does. And that's putting it very simply, because you can see this equation is actually very difficult to solve. So that's why we need a process simulator to solve the model. So why do we need the volume? Because with the pressure, temperature, and volume, these three, we can choose two to provide, and the third will be calculated by the simulator. And from these three properties, we can calculate everything else. We can calculate enthalpy, entropy, density, viscosity, heat transfer, work done, and so on. So basically, you need to input usually temperature and pressure, but it can also be vapor fraction, because vapor fraction will determine the temperature and pressure. And when you do that, HYSYS or any simulator will input the data that it has already stored in the simulator, which is in this case the TC, PC, and this omega for this component. Let's say water, then HYSYS will find out water. What are the three parameters for water? Put into this equation, calculate A, calculate B, then you give it P and T, and then it comes out with the volume. So this is the output that I want. So to put it very simply, this is what a process simulator does. After it gets this value, you can calculate everything else. Density, molar volume, viscosity, enthalpy, entropy, heat capacity, heat transfer, work done, and so on. So to the most basic, this is what a simulator does. But in order to ensure the simulator does the correct thing, I mentioned that we need some inputs. We need the component parameters, the TC, critical temperature, PC, critical pressure, and omega, which is what we call the eccentric factor or eccentricity. You must ensure that these inputs are correct. Otherwise, you get the wrong answers. And this is a term that in IT, they call it garbage in, garbage out, or GIGO. It means that if you put garbage into the computer, computer prints out garbage for you. And that also applies in process simulation. So before you do anything, it's best to sketch out on paper and make sure that you know the overall picture before we start doing the simulation. So I'm just going to show you this very simple thing that let's say I'm a student, I'm trying to do this simulation. All right. I want to know what is the distillate flow rate, what is the bottom flow rate. Sounds simple, right? I have a given feed is 100 kilomole per hour, 50% propane C3H8, 50% by mole butane C4H10. And the specification that I want is to have 99% recovery of propane at D, which is distillate. So I want 99% of the propane to come to the top. 90% of purity of propane at D. So I want the purity to be 90%, which is this one. And let's assume that the simulator has calculated the required thermodynamics, and it tells me that at these conditions, at a certain T, the distillate is 90% propane and 10% butane. So that's what I can get under these conditions. And let's see if the simulator can solve this problem. All right. So the purity spec is already here. So I already have the purity spec. So purity spec is correct. 90% purity at D. Okay. I want 99% recovery of propane at D. So we can first calculate out the input. So we have feed of 100 kilomole per hour, 50% of propane. So we have 50 kilomole per hour of propane. We also have 50 kilomole per hour of butane. I want 99% of this to go here. So you can use a calculator and press 1, and then you get 49.5 kilomole per hour of propane. So this is a unit kilomole per hour. And then this is a 10% purity, 10% mole fraction. So you can calculate that, and that will mean that in theory, I will need 49.5 times 1/9. That means that this will be 5.5 kilomole per hour of C4. So because there are only two outlet streams, right? One is not going out the top, needs to go down the bottom. So it's, let me just press the calculator now. So we have a remaining propane. So we have 50 kilomole per hour inlet, 49.5 going out the top. So 0.5 kilomole per hour at the bottom. It's a spacing mass balance, by the way, it equals out there. And there's no generation, no accumulation, no consumption. So C4 is 50, here is 5.5, so remaining will be 44.5 kilomole per hour of C4. So from here, we can calculate the percentage, the composition of the product. So 0.5 over 44.5 is 1%, 1.12 mole percent. And the remaining with that would be 98.9%. So you can see that, but the thermodynamics say the best I can achieve is this 10%, 90%. But in order to achieve both of these items, I will need to have this separation. very, very perfect, almost perfect separation, 99% between the bottom. So this spec will be unachievable. And you can do it opposite way by assuming that this is achievable, and you can find that this is not achievable. So this is infeasible specs. To get a feasible result, we will have to either sacrifice the recovery or sacrifice the purity. And that this example alone will illustrate most of the problems that you will face when you do simulation, because the requirements that you ask the simulator to do are too strict. You can only achieve one of them. So maybe I had to drop my recovery to 95%, for example. Or if I want 99% recovery, I might have to drop the purity to 85%. And then we can get the result that is logical. So this shows that you have to sketch out the results on paper before you start doing. Otherwise, you don't realize that, and then get very frustrated. Oh, I can't get the result I want. A lot of errors and so on. And in fact, it's actually from the start, this simulation is already impossible to conduct because the specification is not logical. So it's always good to have a big picture view before you do anything.